On November 3, 2002, a colossal rupture tore through the Alaskan wilderness. For more than 2 minutes, a 2,000-mile long strike-slip fault system known as the Denali Fault unzipped the Earth's surface, unleashing a magnitude 7.9 earthquake. The ground itself liquefied. Forests shook. Mountains moved. It was a moment of profound, isolated violence in one of the most remote corners of the continent. And 2,000 miles away, in Wyoming, a sleeping giant stirred. Within hours of the main shock in Alaska, the ground beneath Yellowstone National Park began to tremble, not with one large quake, but with a swarm. Over 1,000 tiny, localized earthquakes shuddered through the rock, clustered in the park's most active geyser basins. Something else was happening. Geysers that had erupted with clockwork predictability for decades suddenly changed their rhythm. Some sped up, some slowed down, some sputtered and died. The signal was undeniable. The ground breaking apart in Alaska was physically altering the behavior of a supervolcano a continent away. Not a theory, not a model. A direct, measured, and terrifying observation. This was the message that flashed across computer screens at the University of Utah seismograph stations, leaving geophysicists staring in disbelief. For decades, the tectonic violence of Alaska's Ring of Fire and the volcanic hotspot of Yellowstone were treated as two separate worlds. One driven by the grinding of oceanic plates, the other by a plume of heat burning up through the continental crust. They were not supposed to be connected. They were not supposed to talk to each other. But the data said they were. The data said the conversation was happening in real time. So now, scientists are facing a much larger question. If a single earthquake in 2002 could do this, what happens next? Because right now, as of July 2026, the signals from Alaska are not just repeating, they are escalating. And Yellowstone is listening. The link was not a fluke, it was a pattern. To understand the signal received in 2002, you have to look back further. To March 27, 1964, on that day. The second largest earthquake ever recorded in human history devastated the coast of Alaska. At magnitude 9.2, the Great Alaska Earthquake was an almost incomprehensible release of planetary energy, causing over 131 fatalities and reshaping the coastline forever. The seismic waves it produced were so powerful they propagated through the entire North American plate like a tremor through a bell. And far away in Yellowstone, tourists standing around Old Faithful noticed something strange. The world's most famous geyser, an icon of natural predictability, suddenly shortened its eruption cycle. The underground plumbing of Yellowstone, its delicate network of fractures and fissures, had felt the nudge from an Alaskan megathrust quake. It had responded. For years, this connection was treated as a curiosity, a strange outlier in the geological record. Then came the Denali earthquake. The team at the University of Utah, led by the pioneering geophysicist Dr. Robert B. Smith, finally proved it was a direct mechanical process. It's a phenomenon called dynamic stress transfer. The massive, low-frequency surface waves from a large earthquake don't just shake the ground. They actively squeeze and stretch the crust as they pass through it. When these waves traveled the 3,100 kilometers from the Denali Fault to Yellowstone, they rolled through the park's vast hydrothermal system. This is a fragile, ancient network of underground channels filled with water superheated by the magma chamber far below. The water is held under immense pore pressure, trapped in the microscopic spaces within the rock. The passing seismic waves acted like a giant hand squeezing a sponge. They momentarily raised and lowered that pressure, dislodging mineral deposits, opening new pathways, and effectively unclogging the plumbing. Dr. Smith himself said it best. We did not expect to see these prolonged changes. He called it the first time an earthquake was known to have changed the behavior of such hydrothermal features at such great distances. Not magma moving, water, not the volcano erupting, the plumbing shifting. It's a critical distinction. The clickbait headlines love to scream that an Alaskan earthquake will trigger the Yellowstone supervolcano. The science tells a different, more nuanced, and arguably more unsettling story. It's not about triggering a single cataclysmic eruption. It's about shaking a system that is already on a knife's edge and waking up processes that we are only just beginning to understand. And that system has its own violent history, before scientists ever knew about the connection to Alaska. Yellowstone proved it could generate its own disasters. On August 17, 1959, a magnitude 7.5 earthquake struck just west of the park boundary at Hebgen Lake. It was not a distant signal, it was a local rupture. The shaking was so violent it triggered a landslide that sent 80 million tons of rock crashing into a canyon, damming the Madison River and creating a new lake overnight. 28 people died. The ground itself dropped by nearly 20 feet in some places, tilting the entire Hebgen Lake basin and sending a massive wave of water, a seiche, sloshing back and forth across its surface like water in a tub. The 1959 Hebgen Lake event was a brutal reminder that the ground beneath Yellowstone is not solid. It is a fractured, heated, and dynamic crust sitting directly on top of a massive heat source. It is primed for disturbance. It is uniquely sensitive to being shaken, whether that shake comes from a local fault or from an echo thousands of miles away. This is the context that makes the current signals from Alaska so compelling. On Mount Kuprianof, a remote volcano on the Alaskan peninsula, something is happening deep underground. In June and early July of 2026, data from interferometric synthetic aperture radar satellites, or INSAR, confirmed it. Scientists were bouncing radar signals off the volcano's snowy flanks from space and measuring the echo down to the centimeter. The ground was swelling. The data revealed an inflating spherical magma source, a new batch of molten rock accumulating 3.7 miles, or 6 kilometers, below sea level. Between late 2025 and mid-2026, the surface had bulged upwards by 10 centimeters. The Alaska Volcano Observatory calculated the volume of this new intrusion at approximately 0.04 cubic kilometers of magma. On May 12, 2026, they officially raised the volcano's alert level to advisory/yellow due to the swelling and an increase in sulfur dioxide gas emissions. A volcano is actively inflating. It is pressurizing the crust, and it is not alone. Far to the west, in the Andreanof Islands, Great Sitkin Volcano has been in a state of continuous, slow-motion eruption since July of 2021. For 5 years, a thick, viscous lava has been pushing its way into the summit crater, a relentless effusion of basaltic andesite. Alaska is not quiet. The tectonic boundary that spawned the 1964 and 2002 earthquakes is active, releasing energy and loading stress into the continental plate. And Yellowstone, 2,000 miles away, is showing its own signs of restlessness. On July 23, 2024, a violent explosion ripped through Biscuit Basin, one of Yellowstone's popular thermal areas. It was not a volcanic eruption. It was a hydrothermal explosion, an event driven purely by superheated water. At Black Diamond Pool, groundwater flashed instantly to steam, expanding with enough force to destroy a tourist boardwalk and hurl rocks and debris across the landscape. The event was a stark display of the power contained within Yellowstone's plumbing. Then, on June 13, 2026, it happened again. A second, smaller hydrothermal explosion struck the very same pool. The system was volatile, unstable. The signs kept coming. In February 2026, after a 6-year slumber, Ekenis Geyser in the Norris Geyser Basin roared back to life. This is not just any geyser. Ekenis is the largest acidic geyser in the world, a rare feature where water as acidic as orange juice blasts from the earth. It erupted around 40 times that month, a sudden reawakening of a major thermal feature in the park's hottest and most dynamic basin. At the same time, scientists at the Yellowstone Volcano Observatory, or YVO, were tracking a subtle anomaly. An area of minor ground uplift just south of Norris had begun in July 2025. Using GPS and INSAR data, they watched the ground rise, millimeter by millimeter. Before the uplift ceased in January 2026, they traced the source to dynamic changes happening roughly 9 miles or 14 kilometers beneath the surface. None of these events, on their own, signal an imminent catastrophe. Yellowstone is a living, breathing volcanic system. It averages 1,500 to 2,500 earthquakes a year. The ground is constantly rising and falling. Geysers turn on and off. That is what makes it Yellowstone. But taken together, in the context of the proven link to Alaska, a different picture emerges, not of a single impending disaster, but of a continent-wide system of connected stress. The loading in Alaska. The sensitivity in Yellowstone. One end of the wire is being plucked, the other end is vibrating in response. And scientists are now trying to understand just what exactly that wire is connected to. The greatest misconception about Yellowstone is that it is overdue for a supereruption, that the volcano operates on some kind of cosmic schedule. This is a myth born from a misunderstanding of geological time, but the definitive rebuttal to this myth arrived in April 2025. From a groundbreaking study that gave us the clearest picture ever of what lies beneath the park, a team of researchers from the University of Utah and the University of New Mexico, led by YIVO's chief seismologist, Dr. Jamie Farrell, accomplished something extraordinary. They mapped the absolute top of Yellowstone's Magma reservoir. Not an estimate, not a model, a precise boundary. Using a technique called seismic tomography, they used mechanical vibration sources to send seismic waves deep into the crust and listen to the echoes with a dense network of sensors. It's like a CAT scan of the Earth. The results were stunningly clear. The top of the main magma chamber is located at a precise depth of 3.8 kilometers, about 12,500 feet below the surface. More importantly, they imaged what Dr. Farrell called a volatile rich cap. This is not just a pool of liquid rock. It is a layer where volcanic gases, water vapor, carbon dioxide, sulfur dioxide are trapped, dissolved in the uppermost layer of magma under immense pressure. As Dr. Farrell explained, this is the number that matters. The depth of 3.8 kilometers is important. We know what pressures are going to be and how bubbles are going to come out of the magma. This is the core of what makes a volcano explosive. It's not the liquid rock itself, it's the trapped gas. When that magma rises and the pressure drops, those dissolved gases come violently out of solution, expanding exponentially. It is the same physics that turns a shaken bottle of soda into a geyser of foam. If gases are trapped, Farrell warned, they become very explosive as they decompress. This discovery does two things. First, it gives scientists the exact depth and characteristics of the real volcanic threat. Second, and just as importantly, it helps them confirm what is not happening. The same imaging techniques show that the vast majority of Yellowstone's magma reservoir is not a giant cavern of molten liquid. It is a mostly solid, crystalline mush, a rocky sponge with only pockets of melt within it. To trigger a supereruption, you would need to liquefy an enormous volume of that mush, something that takes tens of thousands of years of heat input from the mantle plume below. As YIVO's scientist in charge, Michael Poland, regularly explains in his weekly Caldera Chronicles columns, Yellowstone is nowhere near that state. The system simply does not have the eruptible capacity for a supereruption right now. The real danger is not the impossible supereruption. It's the very real, very possible hydrothermal explosions, triggered by the constant shifting and shaking of the ground, like the ones at Biscuit Basin. This constant monitoring has led to accidental discoveries that paint an even richer picture of the park's environment. In May 2025, Yellowstone's network of infrasound arrays, essentially microphones designed to listen for the low-frequency boom of steam explosions from geysers, detected something else entirely. A massive, echoing boom that didn't come from the ground. It came from the sky. The sensors had unintentionally recorded the acoustic shockwave of a large meteor, a bolide, exploding high in the atmosphere above the park. They were listening for the volcano and heard a message from space. Even the cleanup efforts reveal the strange intersection of nature and humanity. In 2025 alone, USC scientists had to remove 343 hats, mostly black baseball caps, that had been blown off the heads of tourists and into the park's fragile, irreplaceable thermal basins. It is a place of primordial power and modern absurdity existing side by side. Stretching between the Alaskan faults and the Yellowstone hotspot lies another quieter piece of the puzzle, the Cascadia subduction zone. This is where the Juan de Fuca plate is diving beneath the North American plate, running from British Columbia down to Northern California. For decades, scientists believed it was seismically quiet. And then they discovered episodic tremor and slip, or ETS. This is a phenomenon where the tectonic plates undergo slow motion, silent earthquakes. Over weeks, the plates will slip past each other by a few centimeters, accompanied by a faint, low-frequency tremor that no human can feel. It is a slow, gradual release of stress, or, as some scientists fear, a sign of stress building toward a future megathrust earthquake on the same scale as the 1964 Alaska event. Networks of GPS stations run by the EarthScope Consortium track this silent slip, measuring the deformation of the continent in real time. This is the creeping, hidden signal passing directly through the land that separates the explosive power of Alaska from the volcanic heart of Yellowstone. It is another part of the conversation. So what does it all mean? The inflating magma chamber under Mount Kuprianof is not a guarantee of a massive eruption, but it is pressurizing the system. The ongoing eruption at Great Sitkin is a constant reminder of the energy in the Aleutian chain. The reawakening of Geyser and the explosions at Biscuit Basin are not signs of a supereruption, but they are proof of the hydrothermal system's hair-trigger sensitivity. The 3.8-kilometer depth of the magma cap is not a doomsday clock. It is a precise measurement of where the true explosive potential lies. Waiting, these are not disparate events. They are data points in a single, continent-spanning story of geological stress. The great scientific challenge of the 21st century is moving from observing these phenomena to understanding their connections. The technology is finally catching up to the complexity. The INSAR satellites that see the ground swell in Alaska are the same tools used to watch the land breathe in Yellowstone. The seismometers that feel the tremor of a distant earthquake are the same ones that map the magma chamber 3.8 kilometers down. The GPS stations of the Network of the Americas watch the entire continent stretch and compress, turning the landmass itself into a single massive sensor. We are in an era of unprecedented surveillance. Every twitch, every tremor, every centimeter of uplift is now recorded, cataloged, and analyzed. But the data does not offer simple answers. It offers deeper, more complicated questions. The connection is real, that is no longer in doubt. An earthquake in Alaska can, and does, trigger seismic swarms and alter geyser behavior in Yellowstone. A fact that was once scientific heresy is now textbook geology. The signal is transmitting. The question is what it's a prelude to. It is not the simple cinematic story of one volcano blowing up. It's the story of a complex, interconnected system humming with energy. It's the story of scientists listening to the subtle conversation happening in the bedrock of a continent, trying to decipher the language of a planet, trying to understand if the rumbling from 2,000 miles away is just a tremor,